Great. So what I'm going to do is now is extend what we've talked about in terms of how we would go about integrating. But before I do, I just want to remind ourselves what we see here is essentially that if I look at this N1 shape function, and I ask you what is the highest order terms present here, what is the highest order polynomial terms present here, we can see is here essentially this is a psi multiplied by eta times a psi, for instance, or an eta times a psi. So what we will see is that there are terms that we most probably there's going to be some constant terms, but there's going to be psi squared terms, eta squared terms, there's going to be psi squared eta terms, and eta psi squared terms, if you just multiply all of that as out. So then you see that's sort of the kind of terms that are present here. So there are pure quadratic terms and there's decoupled third order terms that are present there. Okay, so that's just to make sure that you're aware of that, that be cognizant about that. Okay, so that's just that, and now we can move on and say, if we want to do Gauss quadrature integration, how would we go about doing integration in this world? So what I'm going to do is now, I'm now going to wipe this off. We're not going to be now in this world of wanting to specifically derive another shape function. We just want to ask how would we go about doing Gauss quadrature. Oops, daisy. Let me just. Okay, so that was a miscall. So that's essentially what we have here. And so what we had in the 1D case was, just as a reminder, when we did Gauss quadrature, depending on the number of Gauss rules that we used, but essentially this was the nodal values, and then essentially what we said is we could use a Gauss quadratures at different locations for psi. So let's say it's something there like a 3-point Gauss rule, something like that. We could use those 3 locations, for instance, to do the Gauss quadrature. And what you're going to see is we're going to extend that by saying, well, let's do a 3-point rule in psi and also a 3-point rule in eta. And if we do that, essentially then we can ask ourselves how many Gauss quadrature points are we going to evaluate. Well, let's start off by saying essentially, let's say I've got 3 points here. That's now for this bottom part for eta. That's maybe those 3-point Gauss points that I've got there. Would it be at the bottom line? No, it would not be at the bottom line. It would be somewhere here in the middle. So somewhere here. I'd say there are my 3 Gauss point rules. Okay, because this lowest value that we have here is somewhere in the middle between these 2 nodes. So this lowest value is going to be between these 2 nodes, and then I'm going to extend this idea and say, if I put down a 3-point Gauss rule, I'm going to have to evaluate this thing at 9 places. Okay, so that's essentially that. So this is applying a 3-point rule in the psi direction and applying a 3-point rule in the eta direction. I have essentially the values for, I can't recall what they were, but let's say for psi we're going to have the values of 1 is 1 over square root 3, 0, 1 over square root 3. For eta we're going to have essentially, is this even, no, I think I'm confusing now the Gauss point rules. That's not those weren't the values, were they? What were they? Let me just double check in the list here. What were those Gauss quadrature rules? That's the 2-point rule. Yeah, it's not 1, it's plus minus 0.774, for instance. Sorry, I just want to write here, it's not 1. This is the 2-point rules value. I'm just going to write some other values here. Maybe I should just redo this with that's okay. I'm not gonna, let's just maybe redo this argument with the 2-point rule. I've jumped the gun in my head now with the 3-point rule, so please ignore the 3-point rule. It might be a little bit confusing. For now, let's just rather stick to what we've done in the 2D case. We did the 2-point rule. So essentially I've got the 2-point rule. Those are the 2 places that I would like to evaluate in the 2. Now I can extend this idea into the 2-dimensional case. I'm going to do a 2-point rule. So that's going to be plus minus square root 3 and a plus minus for the psi and a plus minus square root 3 for eta. Okay, so that's essentially what I have. And so when I look at this, I can the various combinations that I have to complete this is going to be psi and eta minus square root 1 3. That's essentially an x there. Then this is negative and this is positive. We're going to have this is positive, this is negative. this positive, and there's my 4 points then. So a 2-point Gauss rule would require me to do 4 evaluations of the stiffness matrix. Okay, if I were to do a 3-point Gauss rule, we have a point in the middle here, then I would essentially have a 3-point Gauss rule here as well required, and I would have to evaluate this at 9 locations. And so you can see a 4-point Gauss rule in 1D, it blows up quite considerably as a 16 evaluations for a 4-point Gauss rule in 2D. So that's the implication of how the Gauss quadrature rules relate. But the same places where we had the weighting functions in the 1D are the same places where we have the weighting function in the 2D, because the difference is in the 1D we had an integral, a single integral of the B transpose dB, let's call it dx, or let's call it d psi, with all the other, there was all the other stuff, the a and the other stuff in there. So let's just write it as, with all the other stuff in there, d psi. And in 2D, all that you have is you have 2 integrals. So the one is in terms of psi, and the one is in terms of eta. And so I also have the B transpose dB, but now I have an eta and a psi integral. And that's really what this boils down to. So I jumped the gun a little bit there in the beginning. I think putting down the 3-point rule first was maybe a bad idea. But hopefully, after you've watched this now, you have a good idea of how the Gauss quadrature integration looks. And that's why it's important that we just keep track of what are the highest order polynomial terms in those expressions that we're integrating, and understanding what the implication is for going for higher order rules in 2D. Things blow up considerably, so things can become much, much slower, because evaluating a matrix at 4 positions versus 9 versus 16, for instance, or then for the 5-point rule, 25 locations, significant differences in computing that stiffness matrix.